Okay, so for this section of Chapter 3, 3.1, this is not going to be a very long video because there's not really much to this section. It just introduces two new topics for you. One of them is scatterplots, and you may have seen scatterplots in other classes, so they shouldn't be that big of a deal. But the newer concept is something called correlation. And once you see it, you'll be like, oh, okay, I kind of get it. And when we do scatterplots in class, I will show you how to do those when we actually get to class, not right now. All right, so here's your objectives. Okay, so if you want to read them, you can read them. We're going to basically go through all this in one video. Okay, so explanatory and response variables. Most statistical studies examine data more than one variable. In many of these settings, two variables play different roles. A response variable measures the outcome. An explanatory variable may help explain or influence the changes in a response variable. So those two seem pretty obvious to me, something we don't really have to go into. So note, in many studies, the goal is to show that the changes in one or more explanatory variable actually cause changes in a response variable. That's the typical goal when you do an experiment in anything scientifically researched. You want to know, is your explanatory variable actually cause changes in the response variable? And then, however, explanatory response relationships don't involve direct causation. Sometimes one can have nothing to do with the other, it just so happens to work out that way. All right, so scatterplot shows the relationship between two quantity variables measured on the same individuals. So if you're talking about the entire population of the school or in the entire population of the classroom, the values of one variable appear on the horizontal, the values of the other appear on the vertical. Each individual in the data appears as a point on the graph. The explanatory variable goes on the x-axis. Okay, and then so when you're drawing this out, actually usually don't have these two coordinate systems here, but usually the explanatory variable goes here, and then your response goes here. Right? And then we plot the data that way. So your explanatory variable is the variable that may help explain or influence changes, and the response variable is the outcome of your study. All right? And it usually looks like, I'm going to show you something really quick so that you can have a better idea in your head of like, what in the world are you talking about, a scatter plot? You've seen these many, many times before. I guarantee it. They look like that. Okay? So just a bunch of points. Data point. For example, this one would be percent taking the SAT. This would be mean math score, right? This is a scatter plot. Okay, so let's move on to the second part. So describing scatter plots is what we really want to get into, because just doing them isn't really going to do much for us. To describe a scatter plot, follow the basic strategy of data analysis from Chapter 1 and 2. We're going to talk about the direction, the form, and the strength of the relationship of the scatter plot. And are there any outliers that you might see? This is not necessarily a situation where you would find the IQR or anything multiplied by 1.5 rule. It's not like that. This is more like visually, can you kind of see an outlier? You could calculate the outlier, but you'd have to do a one variable, not two variables in this case. So, direction, form, and strength. That's what we're going to really be focusing on. Okay, and then we'll throw outliers in there. Okay, so describing scatter plots. Okay, so two variables have a positive association when above average values of one tend to accompany above average values of another, and when below average values tend to occur together. So when your data is more, when you can see that it's got a little bit of a directional form going on, right? This tends to be a positive association going through it. Okay. When it's negative association, when above average values of one tend to accompany the below average values of the other. So this one would have a negative association because as the values here are really low, are really high, then the values here are really low. So eventually you get a negative, think of a slope a little bit, that would help. You have a negative type of association between these values, right? If you had a positive association, it would basically just kind of go the other way. This would be moderately strong. Okay, I'll show you what a strong one looks like in just a second, but this would be a moderately strong. And then you have a couple of choices. So again, we just have negative association, and then the form is slightly curved, and you can see the little curve kind of happening over here. Okay, there's a little bit of a curve going on. Usually it's tense, you can call it a little bit curved, or it can be a linear way. And the important thing is to describe it in a sentence. Okay, so there's a moderately strong negative curve relationship between the percent of students in the state who take the SAT and the mean SAT math score. Further, there are two distinct clusters of states and two possible, that's your key, two possible outliers that fall outside of the overall pattern. The two clusters being like this cluster over here, and then here's another cluster. Okay, and the two possible outliers being this guy, this little dude over here, and this little dude over here. All right, those are possible outliers. We can verify that the old-fashioned way that we do, but not on this thing right now. Okay, so I'm going to write down. I'm going to write down the possibilities. Okay, so if you're talking about strength, okay, in a data set, so just strength. Okay, usually you have either moderately strong. I mean, you can talk about it in terms of, I mean, pretty much from what you see. You can say moderately strong. You can say strong, just in general. Okay, you can say weak. You know, you can say moderately weak. You can say weak. You can say strong. You can say moderately strong. And then you can say, let me think of another one that I used to say, but that's usually about, it. Just strong, weak. I don't really think. Be fairly strong. I mean, pretty much those are the values you want to use. Is it strong or is it weak? And then what varying degree of these is it? That's your question. All right, direction. Okay. We have, let's see, what do we have? We can go, well, the association is going to be, yeah. So we have negative association. We have positive association. Okay. One of those two. Okay. And then form is going to be, is it linear? Is it curved? Is it, I want to say random. Is it random? And you'll see in a second what I mean by that, because sometimes it could be random. It just doesn't have a form at all. So I guess no form would be one of the things. Okay, but you'll see in the next one. Okay, so here's another one. Describing the scatter plot. So you have positive association, right? Because every time your high numbers, your low numbers here are associated with the low number here. Your high number here are associated with the high number here. So they're going in a positive direction. Direction in general appears that the teams that score more points per game have more wins. Teams that score fewer points per game have fewer wins. We say that there's a positive association between the points per game and the wins. This is the sentence that we're looking for. Positive association between points per game and wins. You have to state what positive association between what and what. Form, there seems to be a linear pattern, right? There seems to be a little bit of a linear pattern going on with the graph, the overall pattern follows a straight line. If you think about it, I'll show you guys on the calculator how to figure that out. Because the points do not vary much from the linear pattern, the relationship is fairly strong. So this is a fairly strong relationship. This was a moderately, strong relationship. All right, it was a little bit more spread out than this one is. Okay. And then there do not appear any values that depart from the linear pattern, so there are no outliers. All right. That's direction, form, and strength. Now, that is describing the scatter plot. The next thing we're going to talk about is the correlation. And it's really weird. When we get to class, I'll show you how to look it up on the calculator once you plug everything in. But it's this variable called R that measures the direction and the strength. So how strong is your data without even looking at it? You can actually tell just by calculating a variable. And then it also tells you the direction, meaning is it positively associated or is it negatively associated? Okay, so just by looking at a number, you should be able to tell these two depending on what value you have. Okay, R is always a number between -1 and 1. So when you think of your your axis, think of, zeros in the middle, -1, 1 is here. It could be any number in between -1 and 1. All right. It could be, 0.5. It's always going to be some sort of a decimal with a leading 0 in it. Okay. If R is greater than 0, it indicates a positive association. If R is less than 0, it indicates a negative association. So, for example, positive association R would be, 0.43 or 0.25 or something like that. Okay. If R is less than 0, indicates a negative association, so it'd be something like -0.37 or -0.13 or something like that. All right, so that means your data is going to go in the positive association if your R value, your correlation, is going to be between 0 and 1, and it's going to be negatively associated, so something like this, if your R value is going to be between -1 and 0. All right, and then the values of R near 0 indicate a weak linear relationship. So this would be something like some weak values, -0.04 or 0.13 for that matter. Okay, so values near 0. Okay, the strength of the linear relationship increases as R moves away from 0 towards -1 to 1. So if you have a strong linear relationship, that would be something that looks like 0.97 or -0.85, something close. Well, maybe not 85. 85 is not that strong. 0.92 or something like that. All right. So the closer you are towards -1 and 1, the stronger your association is going to be, or I should say the stronger your form is going to be. I should say your strength in your form. And then the further you are, or the closer you're to 0, the weaker your association. And then extreme values, if it's actually R equals 1 or R equals +1 or -1, occur only in the case of a perfect linear relationship. So think of the most perfect linear relationship possible is literally if your data points are literally in a line going like that. That is the most perfect that you can possibly get, where your line is literally being connected through all of those points. Okay, so that was R. And this is what it looks like when you have different types of correlations. So if you have you have a scatter plot and it looks like a bunch of little tiny dots just everywhere, right? You have of R equal to 0. Okay, so your R value is going to equal 0 because there's absolutely no correlation between your values on the x-axis and your values on the y-axis. Okay, now you have a little bit of a correlation, or you have a little bit of an association between some of the values here. And in this case, the R value is equal to negative 0.3. It's not very strong. Okay. Oopsie, sorry, it's very fuzzy. It's not very strong. Wow, that's so much better. But you can kind of sort of see a little bit like a negative association happening here. Like if I were to draw, let's say, like kind of a line down this way. I'm not separating the data. I'm just maybe kind of like drawing a line to see how close they are to this line. You can see that they're kind of on a decrease, right? So they're negatively associated, but it's still very scattered. And so your R is not going to be very close to -1. It's probably going to be closer to 0, which is what 0.3 gives you. Now, here you have a correlation of positive 0.5, right? So your association's in a positive direction, and they're much better clustered around your line than this one was, but it's still not very close to being, you know, pretty linear like this one is down at the bottom, or this one over here. So we'd say it's about halfway, 0.5. Okay, and then this one, you have a correlation of negative 0.07. There's your negative association. Your data is kind of going in that direction. You have it's not strong. I would say fairly strong, right? I would go with fairly strong. I don't know if I would say moderately strong. I'd say fairly strong. And then the last two are when you really start to see what it's supposed to look like when the correlation is really, or when the association is really strong. So this would be moderately strong, and then this would be strong. Okay. Anytime you get something close to 0.999 or 0.99, negative or positive, it doesn't really matter. You have a pretty strong association between the datas. Okay. Now, the next slide might kill you, but this is how you actually calculate it by hand. You take 1 divided by, let's see, sorry. Suppose that we have data on variables x and y for n individuals. The values for the first individual are x1 and y1. The values for the individual are x2 and y2. And so on and so on. The mean and the standard deviation of the two variables are the x bar and s of x for the x values, and y bar s for the y values, because you basically have to find the standard deviation and the mean for the two separate sets of data, one for the x-axis, one for the y-axis, because those are both variables. And then you do a bunch of work for it, and you get what your correlation is. Now, the calculator will do this automatically for you, so you're in luck. You don't really have to remember this. This is not a requirement. You only have to understand how to interpret the R value, which goes back to what we were talking about over here. Now, facts about the correlation. Okay, how correlation behaves is more important than the details of the formula, right? That's the details of the formula is not that big of a deal. It's what it does that's more important, and how to interpret it. Correlation makes no distinctions between explanatory and response variables. R does not change when we change the units of measurements on x and y or both. It usually kind of stays the same. The correlation itself has no unit of measurement, right? It's not like, 1 point, or I guess we can take this example. It's not 0.5 inches. We're not talking about like standard deviations away from your mean, or we're not talking about, how many inches, it takes for every something. It's just a variable. And once we get the calculator in place, I'll show you what it really means. Okay, correlation requires both the variables be quantitative, right? You can't have qualitative. Does not describe curved relationships between variables, no matter how strong the relationship is. So for the one that we did first, the one that was slightly curved, like this, okay, an R value, whatever it might be, is not the best thing to use to talk about the association between the data points, because the data is kind of curved. but you could still get some sort of a correlation between the two. It's just not the best thing to use because your data is curved. You want it to be as linear as possible before you start talking about association. Okay? And then correlation is not resistant or is strongly affected by few outlining observations. So if you have outliers, it will mess with your correlation. It tends to pull your correlation up or down, or depending on where your outliers are. Okay? And correlation is not a complete summary of two variable data. We're going to get into that a little later, but it's just one piece of talking about the data itself. All right, so let's talk about this one. For each graph, estimate the correlation R and interpret it in context. Well, there's only one graph, so we're just going to do this one. So when you look at the data points, automatically you can see that there is not much of a strong linear relationship. So the next question is, well, how do you know what it might be? So I kind of just go back to this one and I say, okay, well, I can't really see that this is much of, a linear in either direction, either decreasing association or increasing association. It really looks more like this to me, R equals 0. But I'm not super sure, so I would just say, okay, well, let's say that it would be something like, I don't know, kind of like that. Okay. It would probably be closer to 0. So I would say that my estimate would be, I would say it would be around, let's see, what's my prediction for this? My prediction would be, okay, so we have in general, I'm going to try to see how I can write this up really quickly without getting too crazy involved in this. So based on the scatter plot, the correlation, I can't spell correlation to save my life. Correlation R could be approximately close to 0.01, negative 0.01. I don't know. That's my interpretation. So we have a little bit of a negative thing going on. It's very close to 0, right? I don't want to go too far up. So based on the scatterplot, the correlation R is approximately close to negative 0.01, which indicates there is almost no association between last year's percent returns and this year's percent returns. Okay, sorry. So based on the scatter plot, the correlation is approximately close to negative 0.01, which indicates there's almost no association between last year's percent returns and this year's percent returns. Okay, so, and interpret in the context, meaning finish out the sentence and use, the labeling for the x-axis and labeling for the y-axis. Okay, so now it's your turn. Your turn, basically, to estimate and interpret in the context of the question. So here is the info. So scatter plots below show 4 sets of real data. A repeats the manatee plot from figure 3.14. B shows the number of tropical storms versus the number of storms predicted versus observed. C plots the healing rate in micrometers per hour for 2 front limbs of several newts in an experiment. Apparently newts regenerate their limbs. And then D shows the stock market performance in consecutive years over a 56-year period. For each graph, okay, estimate the correlation R, then interpret the value of R in the context. So A, B, C, and D, this is what I want you to do on Canvas. Okay? You just need a sentence, basically, for each one, right? Because you're going to tell me is, what do you think the correlation is, and what does that mean about the data? Is it moderately strong? Is it, positive association, negative association? So you want to talk about, is there somewhat of a relationship between your explanatory variable and your response variable? All right. So there's the 4, if you can see them very well. So here's the first one. Okay, here's the second one. Here's the third one. And then here is the 4th one. Okay, which actually I just did this one. Hey, look, I just gave you a freebie. Okay. All right. Any questions? See me. But that should be the end of it. And I'll see you guys later.